Then we can look at local systems. So now we are actually stepping into DG category territory. And, well, maybe I should start by defining what a local system is. So objects are vector bundles on M with a flat connection. Nabla. Flat just means that it has no curvature. Then we can define the n morphisms between two vector bundles E and F to be, well, we want differential forms, and we want those differential forms to be bundle valued, namely take values in the Hom bundle between E and F. What this means is that we are looking at sections of the bundle. We have the n times alternating product of the cotangent bundle tensored with the Hom bundle. Meaning that we can sort of write every element of this Hom set locally as the sum aij tensor omega ij, where aij is some sort of linear map and omega ij is some sort of n form. And we have a composition operation on there. If we have S in more n fg and t in more m ef, then we define S wedge t to be, well, if we can write S locally as aij tensor omega ij, and if we write t as bkl tensored with eta kl, then we can locally write this as sum over ij kl. Then we have aij bkl, meaning this is sort of the composition of the linear maps tensored with, and now we take the wedge product of these differential forms. And lastly, we have to specify our differential, and our differential is now going to be the exterior derivative, or the exterior covariant derivative, because recall on our vector bundles that are objects, we actually have a connection, and we haven't used that one yet. So we had better get cracking then. So the exterior covariant derivative, we are also going to write this as d, and d applied to some section that we again write as aij tensor omega ij. This is the same as, well, we want this to sort of obey the Leibniz rule. So locally we can write this as such. Now, well, d is linear, so we can pull out the sum. So by the Leibniz rule, what is the only thing that this can reasonably be? Well, first apply, well, not d, but the connection to ij. Now we have a 1 form, and we can wedge that with omega ij. But we can also let our d sort of jump over the aij and get aij tensor d omega ij. And this is it. Well, now you might wonder what I mean by this connection, because aij isn't actually a section of E or G or whatever. aij is a section of the Hom bundle of E and F, for example. So what is the connection on that bundle? well, what we mean by this is the linear map that when we insert a section of the vector bundle E, let's call that one E, this one is equal to the connection on the vector bundle F applied to the section aij, which is now a section of F, minus, and now we have aij applied to the connection on E applied to E, meaning that if the connection measures how much something curves around, then the amount of curving that a linear map does is the amount of curving that its result does minus the amount of curving that its input already did. And, well, it is a bit of work to check that all of these together actually define a DG category, but they do. Important observation. If we compose this exterior covariant derivative with itself, usually you wouldn't expect it to be zero, because, yeah, sure, you have this exterior derivative here, so that will turn out to be zero, alright. But what about this connection here? It turns out, in general, this, when applied to some section E, will turn out to be the curvature of the connection on the vector bundle wedged with E. However, note that since we're working with flat connections here, this induced connection on the hom bundle has actually no curvature, so this is zero, meaning that the D indeed squares to zero, and yeah, furthermore we can show that because the connection and the exterior derivative both satisfy the Leibniz rule, that our exterior covariant derivative also satisfies the Leibniz rule. So all in all, the category of linear systems on a manifold M indeed is a DG category. And there is an important special case. We can look at a subcategory of that category, namely look at the full subcategory of LSM consisting of the trivial line bundle or the trivial one-dimensional vector bundle that, well, is a category with just one object, so it is a DG algebra. And when we look at it a bit more closely, we see that indeed the n forms in the bundle and R are just the R-valued n forms, or in other words, just the n forms on our manifold M. Which means that as a special case of this DG category, we recover the DG algebra that we already saw as an example.